Welcome, everyone. This is another session in the Z Performance and Capacity stream. Today we have Scott Chapman, who is going to present How Busy is That Mainframe Really? If you have questions for Scott, please feel free to drop them in the chat. He and I will monitor those. And we ask you to, one, remember that all these sessions are being recorded, and two, please submit your session feedback at the end. There'll be a link on the last slide. So with that, I'll turn it over to Scott. Welcome, Scott.
Okay, thank you very much, Donna. Alrighty, so how busy is that mainframe really? We'll see how really we can get done in this in 45 minutes here. I think we'll be fine though. But if I ignore your question, if it pops up in the chat, know that it's probably because I'm running on time, or I'll just get it at the end. So this is the abstract, which I'm sure you're all read, which is why you're actually here, right? And then this is our agenda, which we'll get through. If you don't know who we are, Enterprise Performance Strategies, we do ZOS performance. We have a performance reporting tool called Pivoter. We do education and instruction. We teach classes. Now they're pretty much all virtual, but we do that. We do a little bit of consulting, and of course, we present at great conferences and virtual conferences like this as well. And we do our own webinars too. So if you're interested in ZOS performance, hit up the website, get signed up for the webinars. Those are free, happen every couple of weeks for the most part. So there we go. Okay, so let's delve into this topic though. So the first question is, do we have a problem, right? So this is your standard machine busy chart, Keck busy chart. This is for the general purpose engines. And so this is just your RMF intervals over the course of the day. It looks like this particular customer, we must have data from 6 a.m. to 6 a.m. And these are, your typical 15-minute intervals. You got your different LPARs. They're all stacked up here. And so we see, yes, this machine is peaking out, looks like overnight here, above 90% busy. During the day, it's less than 80% busy. So, you probably feel reasonable about this. This looks like a reasonably reasonable situation we see all the time, right? Not so busy necessarily during the day, peaks overnight when they got a bunch of batch coming in. Okay, fairly common. Here's another machine. This one, just point out, actually is midnight to midnight. So this is our daytime hump. Again, another relatively common pattern. Here they don't have quite as much batch. Their batch is more limited. They're peaking during the day. That peaking is less than 80% busy. We know that they're on a 5-way machine here. So they're a K05, so they have 5 CPs. And so, if you're 80% busy on a 5-way machine, that means on average, 1 CP is not doing anything, right? So this seems pretty good. In this particular case, they have 1 dominant LPAR and one minor LPAR. And then if we look at this machine, it's kind of a similar pattern. There's a little bit more, there's some more spikes of batch, but again, during the day, they're peaking at less than 80% busy. In this case, it's a 712, so it's a 12-way machine. So there's at least 2 engines that are unbusy all day. Again, this seems like a pretty reasonable thing. So most ZOS performance and capacity people would probably say those machines are just fine from a capacity perspective. And probably they mostly are, right? There's these long-standing mantras, though, that I think are interesting because they're not necessarily always true, right? So there's this long-standing mantra of you can run the mainframe 100% busy, unlike those other servers that only run at 10% busy. What's usually left off from that is the part about assuming that you have some sort of mixed workload and some sort of work that is okay to delay somewhat, right? The other part of that too is that not everything that can be done should be done. What do I mean by that? Well, in this particular case of the 100% busy thing is that just because you can run your machine at 100% busy, and just because your loved ones, your workloads that you want to perform the best probably are still going to perform okay. That doesn't mean that they're necessarily going to perform optimally, or that you will consume the least amount of CPU per business function. Running your machine at 100% busy actually means that you will probably consume more MSUs than if you had a larger machine that you were only running at 70 to 80% busy. And that becomes a problem from a software cost perspective because you're consuming more CPU. You pay for your software based on the amount of CPU you consume, either under the rolling 4-hour average or under the total MSU hours under TFP. So just because you can run the machine at 100% busy doesn't mean that you necessarily should run it at 100% busy every day, all day long, especially. The other point here is that LSPR testing is done around 90% busy. So when you're running above 100% busy, again, you're not getting all the MIPS out of the machine that you would necessarily expect. But in general, this is true, right? You can run the machine 100% busy, and and it works a lot better in the mainframe world than it does on those other servers that you may be familiar with. Running those machines at 100% busy, you will probably find interesting problems. Now, the final point, though, here is really what I want to talk about today, which is, can you have performance problems despite only being 80% busy? And if so, can we determine where those performance problems came from, what was involved in those performance problems? So here's that first machine again. Again, this looks like it's relatively busy during this particular time frame and not busy over here, right? Well, here's a slightly different view about that. And this view, first of all, looks a little more alarming because we have a lot more red on the chart, and we're going to assume red is bad, right? And what this report is actually doing is showing you the distribution of the interval where the machine was at different percentages busy, right? So the very dark red here means the machine was 99 or 100% busy during some portion of the interval. And so when we look at this big red bar here for these two intervals, that says the machine was actually at or above 99% busy for actually, it looks like over 50% of the interval. So these are these 15-minute RMF intervals, but now we get a sense for the distribution for how busy the machine was over the course of the interval. Instead of looking here, and you're looking at this total, this is really just an average over that 15-minute interval. Here we now start to see some of the distribution of how busy it was over the interval. So where does this come from? That previous report comes from the SMF 99 subtype 12 data. That data is the hyperdispatch detail data, which is cut every 2 seconds. And this data happens to include the CAC utilization. Now, it's cut at we have 2-second intervals here. The records actually are only written every 10 seconds. But the point here is that we get 2-second level detail, and you can hide many fewer problems in 2 seconds than you can hide in 900-second intervals. It's still an average over the course of those 2 seconds, but a 2-second average is a lot different than a 900-second average. And that distribution report just basically summarizes those 2-second averages, 2-second measurements into those 15-minute RMF intervals. So what if we look at those other two machines? Again, here we look like we should have no problem here. But if we actually look at the distribution, there's a bunch of red here. Now, to make this a little bit easier to read, what I can do is I can turn off all the intervals below 90% or all the measurements below 90%. And now it's a little easier to read what percentage of these intervals was the machine above 90% busy, right? Because we selected just these three percentage distributions here. And so what we see here is like right here, you can see, oh, well, 20% of the interval. So 20% of a 15-minute interval is 1/5 of 15 minutes is 3 minutes, right? So there was at least 3 minutes in these intervals here where the machine was actually over 90% busy, instead of when we looked back here, it looks like we were less than 80% busy. So that's a completely different story, right? That you may think a little bit differently about. And here's that 12-way machine, just to finish these off. Again, this looks a lot better, but there's still some pretty big chunks of red in here at times, right? And if we, again, get rid of the ones we care less about, we do see that there are times, again, where we're 20%, even almost 50% of the interval, where we're above 90% busy. But, you know, a little less evidence than on the 5-way machine, as we'd expect on the 12-way. Now, would you care? In many cases, you might not, right? If you're not having a problem, sometimes it's better not to look for a problem. So that's great. If your phone's not ringing, maybe you don't necessarily care about this. But sometimes there are brief mystery problems, right? That can last from seconds to minutes. I say minutes to seconds, but either way. And those 15-minute intervals in RMF can hide a whole lot of those transient problems. It can make it very difficult when somebody calls them and says, hey, the system just seemed to lock up at, 9:07 this morning. And you go look at your RMF interval from 9 o'clock to 9:15, you go, we're 70% busy. I don't really see any, the delay samples are good. Everything, I don't really see a problem here. Well, if we could actually zoom in to a much finer level of detail to get down to, a sub-minute measurement, we might be able to find out what's going on there. And sometimes those transient backups can cascade into a broader set of problems. And maybe you can see evidence of those broader set of problems, but you would like to be able to identify where did this start. Again, having some level of detail below the 15-minute interval can be very helpful. You may have also heard, well, the WLM policy really only matters when the system is busy, and we're not that busy. We're less than 80% busy all day long. And while that's mostly true, you're probably busier more often than you think, right? As we just saw. So the point here is, do not assume you have no CPU problems just because you're only at 80% busy when you look at your 15-minute RMF intervals. Because within that 15-minute interval, there could be multiple minutes where you're running 100% busy. All right, so let's take a look at some of these transient performance problems and how we can actually look for those problems. So the SMF data actually does have useful information for us for doing this sort of transient performance analysis. First off, there's these transactional records that are cut for CICS, DB2, WebSphere, other address spaces, and like the 110s, the 101s, the 120s, et cetera. These are often you can get a per transaction level of detail, right? So per CICS transaction, per transaction coming into DB2 or WebSphere. These can be very voluminous. I mean, hundreds of gigabytes a day are quite possible. We're really not going in, and we're not going to go into the details of what's in those records and analyzing those records in this discussion. But just know that they're there. And especially if you're doing application level investigation, they can be quite useful. The SMF 98 data is relatively new. Those are the high frequency throughput statistics. And they also have specific records for the IBM product, the workload interaction correlator. These are cut at a customer defined interval of 5 to 60 seconds. I say mostly here because if you don't use a 5-second interval, you'll may be surprised when you look at the data and find that there are 4 minutes out of the hour where they actually are cut on the 5-second interval. So the IBM recommendation is to cut these at 5 seconds. Has always been the recommendation, I believe, out of the Washington Systems Center. I believe when these first came out, the default might have been 60 seconds. My initial reaction on that was, hey, if you're a little bit worried about this, turn them on, set them to maybe 15, 20, whatever, and see how it goes. Today, I'm kind of with the WSC and say, you know what? They're good enough information and they're not voluminous enough to worry about it. Just set it to 5 seconds and don't worry about it. It also makes some of the charting nicer too, as you'll see later in this presentation. The SMF 99s have been around since literally 1995 when WLM pretty much first came out. It might have not been GA day one, but it was very close to day one. These are SRM and WLM decisions. These are mostly at 10-second intervals, but there's some subtypes like the subtype 12s, which come out at 2-second intervals. So these have gotten a bad rap over the years because in 1995, when they were introduced, the IBM recommendation was, oh, don't cut these because they're too voluminous. What was voluminous in 1995 is very different than what is voluminous 30 years later in 2025, right? So that recommendation, which may actually, I think actually is still in the manual, even in ZOS 3.1, really doesn't make as much sense today as it may have made in 1995. So what are we talking about in terms of data volumes? The transactional records are really based on the transaction volume, but can be easily tens to hundreds of gigabytes of data per day. However, most customers are already cutting most of those transactional records today, and yet many customers don't cut the 98s and 99s, despite those records only being megabytes instead of gigabytes. So I think that's really something that this is my new thing to champion is go cut the SMF 98s and 99s. If you want, I have more detailed volumes. You can go look at the end of these at the end of this presentation. But if you're cutting 98s for a 5-second interval, you're probably talking 400 to 500 megabytes per system per day. So megabytes, half a gigabyte. For the 99s, today my minimum recommended subtypes are the 6, 8, 10, 11, 12, and 14, and you'll never see a 10, or you should never see a 10 because those only come out if there's been a hardware failure. So these will total to about 100 to 150 megabytes per system per day. So really very minimal. Now, the additional recommended subtypes would be the 1, 2s, and 3s. These will get you up around that 1 gigabyte mark, maybe up to a gig and a half of data per day. But the 2s can be especially quite interesting. So my recommendation, again, for a gigabyte and a half of data a day, these I would like to generally see turned on as well. Now, what can we see out of this? Well, let's take a look at some examples here. So here, this again comes from the 15-minute RMF interval. Here, I'm looking at I've turned off other things, and we're just focusing primarily here on the MVS busy, which, if you don't know, is really a logical view of how busy is the logical processors on the machine. Oh, there was a question that said, when you say per system, what do you mean? I mean per LPAR, per ZOS image. So good question. The 73% here is basically a logical busy number. I also left the capture ratio up here, but that doesn't really matter so much at the moment. But it's nice that they have a good capture ratio. We're going to focus on this time frame right here. It looks like it's about 3 o'clock that's where we're at 73% busy. Now today I don't worry about MVS busy much anymore because people have generally low pool processors. And so back in the day when we were very closely managing the number of logical processors on an LPAR, sometimes you'd bump up against your number of logical processor limit, and then that would be a problem. And, we have less of that problem today, again, because for the larger LPARs, generally, we have some low pool processors that they can borrow then capacity from the other LPARs, and it's usually not a major problem. However, sometimes it is still interesting to look at. And in particular, if we take this 15-minute interval here where it looks like we're only 73% busy, and we go look at this on a 2-second basis for how busy MVS was. So this again is the MVS busy number. We see there's a much different pattern here, right? And in particular, if you look at the beginning of this interval here, which looks like it was about I don't have it written down there, but it looks like it was about 15:02 here to 15:04. So for a couple of minutes here, we actually were running out of logical processor capacity, right? So we were very busy during these couple of minutes. The average here drawn across, if I probably should have drawn that line across here, but at 73%, you get that 73% over the course of the 15-minute interval because there was a bunch of measurements where you were actually much below that, but this was kind of a problem time here. It looks like there were some other brief spikes in here as well, but we're going to primarily focus on this time here. So the next question is what drove that, right? And we can see what drove that if we look at the 99 subtype 6 data. So here again, I'm focusing just on approximately that 15-minute period here. You can see here's 15:01 over here, here's 15:15 over here. And what we're seeing here is 10-second interval based data out of the 99 subtype 6s. And so in the 99 subtype 6s, we get utilization on a service class period basis because that's how WLM manages the work. And so here's all of our service class periods. And what we can see here is that DB prod and prod bat low seem to be the things that kind of, contributed to a difference in that couple of minutes where we're running out MVS busy. So now we have service classes that we actually could go, oh, okay, well, my guess is there was something that came in from batch. So batch started up. It was consuming a bit of CPU, but was driving a bunch more into DB2, and hence the reason why we got busy during those couple of minutes. Now, if there's a particular question about a particular service class, we can also dive deeper in the 99s. This is now a different service class period. In this case, we're now looking at DB2 STP. So it wasn't the problem, right? But it was one of the other workloads that was running on the system. The interesting thing here is this is our service accumulated above and below chart. I came up with this several years ago, and turns out Peter really loves this chart. I mean, I like it too. I came up with it, but the idea of this chart is to give you a sense of where is this workload running in terms of dispatch priority relative to the other work on the system, and we can see that DB2 STP is in blue here. That's this service class period, and it was running relatively low in the dispatching priority order. Now the yellow here is equal priority work. So whatever dispatching priority this was, there was a bunch of other work running at the exact same dispatching priority. But overall, there wasn't much running below it, right? So there wasn't much displaceable work below it. And then all of a sudden, interestingly enough, right around the time that we got busier, because you see the total CPU service did go up in this 10-second interval here, when that happened, concurrent with that, the relative dispatching priority of this work actually went up as well. Or perhaps the opposite occurred, right? That the work that came in at a dispatching priority below this work, which in this case would be goodness, because that means that protects this particular workload. So it basically moved up. Now, did it move up because WLM moved it up, or did it move up because the work that came in was below it? Well, we can actually look at that too out of the 99s. So here, what we see is the dispatch priority is in blue up here again for that DB2 STP workload, and what we see is actually it did move up in dispatching priority here. And why did it move up in dispatching priority? Well, here's the PIs, and WLM actually records two PIs, a local PI for the system that's running on, and a sysplex PI that is across all systems in the sysplex. And what we see here is that this data in the 99s is recorded on a scale basically multiplied by 100, because in the SMF data, we don't like recording fractions. So this 100 is really a PI of 1. When you're below a PI of 1, that means you're overperforming. So this work was actually overperforming which is probably why it was near the bottom of the dispatching priority, right? And then all of a sudden, it was underperforming. Its PI went above 1 or above 100 on this particular scale. And so because it now is suffering relative to its goal, WLM actually did move it up in terms of dispatching priority. Well, there's my circle for what we're looking at here, right? So this is very nice. I love this because this is a great example of, look, WLM noticed the work is no longer meeting its goal, probably because that other work came in, as we saw, and then it bumped up the dispatching priority of this work to try and help it out. Okay, so here's a different example. This is a completely different system, different time here. In this case, we see a sharp increase in both system and STC high work at 906. And so we may be interested, well, what's in there? Or is this causing a problem, right? And in the 99 subtype 2 and the subtype 8 data, we can actually see CPU delay sample counts. And here, what we see is that CICS MRO, which I probably should have drawn an arrow for here, is this purple workload. And you can kind of see, yes, there was an increase in delay samples across multiple workloads, but especially CICS MRO, when these workloads got busier, right? And remember, these workloads are system and STC high, system being the top of the heap. It's the most important work in the system. The STC high, I'm guessing, is also very important and probably has a relatively high dispatching priority. And sure enough, when those things came in, other things did suffer, as we'd probably expect, right? Oh, and this is just, so the 99 subtype 1s are the WLM trace records, if you will, and basically tells us, gives us a little bit insight into what WLM is thinking, if you will, about what actions to take. And what we see here is right around that time frame there. There were at least 3 policy intervals, 3 of those 10-second policy adjustment intervals, where WLM identified CICS MRO as a goal receiver candidate. In other words, WLM was thinking, this thing needs help. Let's see if I can help it. Now, this is just I just wanted to highlight this. We didn't actually dive into, well, did it help it? How did it help it? All that. That sort of information is in there as well. But we're not going to go into that today, but just know the information is there. Okay. So let's take another example here. So here is an example of a machine that here at 1630, we see the machine running 70% busy. Again, it's a U05, so it's a 5-way machine. So from these 15-minute interval data, not really a problem, right? And in fact, if we look at here at the MVS busy number, again, doesn't look like a problem, especially since there are other intervals where, it's even higher, right? So again, not really looking like a problem. You will, of course, now not be surprised to hear that the machine was, in fact, 100% busy for part of that interval, right? So, and that interval is actually this interval here. Again, not the worst interval that we have necessarily, but the interval that we're looking at for this particular example. And again, if we look at the hyperdispatch KEK utilization, again, 2-second by 2-second basis here, we can see, oh yeah, look at that. There was a couple of minutes here right around 1635 where the machine was in fact, quite busy. I left the zips on this chart too. So this chart, we get both the GP utilization and the zip utilization. We don't care as much about the zip utilization here. I think I just left it kind of as a demonstration that that's there. And here's the logical MVS busy. And again, we see that it's running high during that time frame. The orange and green here are interesting because it's the thresholds for hyperdispatch to park and unpark processors, right? So that's interesting because, hey, we go above the green bar, so then we hyper dispatch thinks it may be time to unpark a processor, and when it comes down, it's time to repark that processor, right? And in fact, we can see that in the processor counts as well for whether the how many low processors are parked and unparked. Again, this is on a 2-second basis. This is again on that 15-minute interval that we were looking at. And in fact, we see that here, it came in, it unparked a processor, then it unparked another one, and then apparently it took it away for a couple of seconds and then put it back. The interesting point here too is that hyper-dispatch will only park or unpark one processor every 2 seconds. So as time goes on, it does take, multiple of those 2-second intervals potentially to unpark multiple processors to bring additional capacity to bear. Every 2 seconds is pretty darn quick. So usually that's not a problem. But if you have something that is very, very sensitive to, again, things now down to sub 2-second response time type of things, just understand that is the behavior that happens there. Okay. So stepping away from the 99s and going over to the 98s, we can start to see interesting things in the 98s around these time frames. In particular, how long of a queue do we have, right? So this is an average queue depth by priority bucket. The priority buckets do change in terms of what do we mean by that, and we'll see that in just a moment. The other thing on this chart I want to point out is that in this particular system, the system is using a 15-second high frequency throughput statistics interval. So these are all 15-second intervals, but you'll notice the bars are thinner here at the beginning and the end. And that's because, again, ZOS forces it to a 5-second interval kind of on those 15-minute marks. At minutes 0, 15, 30, and 45, you get data at 5-second intervals, even if you specified 15 seconds for your HFTS interval. And we can also see how much delay we're getting across those priority buckets as well. Now, unfortunately, like I said, those priority buckets do vary. We do have a visualization of that. It's not the greatest visualization in the world, I realize, but it does give us a sense for what are the dispatching priority ranges for the high, medium, low, and discretionary. Discretionary will always be down here. And then, it's kind of the low and medium, and sometimes high, but primarily low and medium that you might see change. This is this is relatively common where they'll go for long periods of time where they don't change and then they do change. It is kind of annoying from the perspective of, hey, it'd be nice if the priority buckets just stayed the same, but because WLM's changing priorities all the time, because there's things that have to happen like unbunching and stuff like that, it makes sense that the priority buckets would change. We also get to take a look at things like preemptions. So here we have preemptions per second, again, by those priority buckets. And these preemptions come in two forms, a major and a minor preemptions. WLM is WLM. ZOS is a fair share dispatching and reduced preemption type of dispatcher. And what that basically means is if you have a unit of work running at a given dispatching priority, when a higher dispatching priority unit of work comes into the system and needs to run, that low priority unit of work will not be stopped immediately. So it's allowed to complete at least its minor time slice before that higher priority unit of work will actually take precedence and cause the low priority unit of work to be undispatched. That's your reduced preemption. And then the fair share side of that is, well, if there's equal priority units of work running, those units of work should be allowed to get some sort of time slice. Their major time slice is what that's called. before they give up the CPU, are forced to give up the CPU to an equal priority unit of work. So this is interesting stuff from the perspective of, you can see how often that you have preemptions happening in that dispatching chain uh, for, again, equal priority and higher priority, sorry, units of work. So interesting, mostly from an educational perspective and from the perspective of understanding that these things are happening on the system. In terms of diagnostics, maybe a little less so, but definitely interesting from a educational perspective. This can be more of a diagnostic. This is the spin lock time, again, in the 98s. Useful information on rare occasions, right? Generally a little less useful for most of the problems that we're looking for. Okay, so now here, and I forget, am I on did I switch systems? I did switch systems here. Okay, so here we have system and STC medium in our blue and red here, getting busy for about 1 minute right at the top of the hour here, okay? Now, that may be interesting, and maybe we'd like to know what address spaces are involved, because there's a bunch of things in STC medium, there's a bunch of things in system. It'd be really cool if we knew why this was occurring, right? Well, if you've turned on the SMF98 records, then we can in fact see what might have been involved. And in fact, the big number here that looks like it's much larger than the other ones is HSM. Whoops, that's all I wanted. Okay, so here we see that DFHSM was involved. That was the STC medium. Okay. Because yeah. And then here on another chart a little further down, that's what it is. Okay, here we see that catalog and XCFAS were also involved. And those were probably the system things that were involved here. So now we got kind of between these two, we kind of have a theory, right? So HSM got busy, that probably drove catalog. Catalog also probably drove some XCF AS. So what HSM was doing exactly, we don't know, whether it was doing space management or was doing recalls, hard to say, but at least for that minute, we at least now have address spaces that we know where that CPU was. And we get that out of the 98 data. Now, the issue with the SMF98 address space data is that only some address spaces are recorded each interval. And basically, it's the top address spaces in some bucket and sub bucket. And it is frankly confusing. And I'm not going to go into all the detail here, especially since today I don't remember that exact detail. I can tell you, though, that they're even recording the same address spaces multiple times because of the sub bucket and bucket concept here. And they didn't come ask me how to do this, obviously. I would have suggested something a little bit different. So notice that the lack of data for an address space does not mean that the address space was not using CPU. It probably just means that in that interval, something else was the top address space. CPU seconds are recorded. So in the 99s, we get data in service units. Here in the 98s, we get it in CPU seconds. Interestingly, the zip time is normalized to GP time. So if you're on a subcapacity machine, make note of that. And of course, the HFTS interval is user selected from 5 to 60 seconds, but on the quarter of the hour, it becomes 5 seconds. So if you're using a interval that's greater than 5 seconds, be aware that what you'll see is this precipitous drop in CPU consumption at the top of the hour, and it looks like there was a problem here, right? And the answer is no, there really wasn't a problem here. What really, I mean, okay, it looks like, hey, TCP/IP was consuming, this much CPU, and all of a sudden it was consuming a whole lot less CPU. And that's really probably not what happened here. What really happened is, instead of recording this on a a 15-second basis or a 20-second basis. I don't remember what this was. It's now recorded on a 5-second basis, and that's why you see it drop. It looks like to about a third of what it was before. So that's the point here. Also notice we have these, this brown is master here and the green is VTM. And it seems like they're discontinuous and they come and go. They're probably really not idle and not consuming CPU here. It's probably just something else was busier in their sub bucket during those intervals. So again, this data is a little bit chaotic, but it can be useful because you can find things like, oh, look, hey, here's HSM that was busy during that particular time frame where we had that spike, right? Also, I should point out too, you may be looking at this going, oh, it's CPU seconds, but it's like 1 to 2 CPU seconds. That doesn't seem like a whole heck of a lot. Yeah, but remember, these are 5-second intervals, especially in here, right? So 1 CPU second in 1 5-second interval basically means I was using 1/5 of a CPU's capacity. And here we're getting we're getting up to close to 2, which would be 40% of a CPU. So you have to recalibrate your brain a little bit to remember, oh, what interval am I on and how many that CPU seconds looks like a small number, but relative to a small interval, it can be a significant portion of a CP. Okay. Ah, perfect timing here. So do we really care? Again, most days you don't care about this level of detail. Most days you're going to take a quick look at your high level reporting on a 15-minute basis and you say, it's all good, right? And look at your application response times. Application response times are meeting my goals. Everything's happy, right? But if you're investigating a problem, having this level of detail available to you, again, primarily from the 99s and 98s, can be very, very useful. Understanding when those low pool processors get parked and unparked goes to how many things can be actually running in your LPAR simultaneously, because you have to have a CP to be able to run something, right? A CP can only be running one task at a time, setting aside SMT on zips and all that. So if the LPAR only has 1 or 2 logical CPs dispatched to available to it because the others are parked, well, then that's not going to be great. And they'll always have 2 as long as you have at least 2, but that side. The queue depths and the dispatch delays can help us understand why things are delayed, because you will see delays even on things like system and STC, sys-STC, and that's because of queuing, right? And again, hey, you only had maybe 3 CPs available on this LPAR, but you got more than 3 address spaces that want to run. So, and this can also be indicative of latent demand. So that's an interesting thing as well. And then, of course, the sub-minute CPU measurements of the service class periods and address spaces can help determine when an issue started and stopped, and also determine what was consuming CPU, possibly at the expense of something else. So in summary and best practice, your machine is probably busier than you think it is more often than you think it is. You might want to consider whether the 15-minute RMF interval is still good in today's world and today's environment. There is some, the vast majority of customers, 90% of the systems that we see have 15-minute RMF intervals. We occasionally see some with 10-minute or 5-minute RMF intervals. I know I've talked to some people who have said, hey, 10 is probably where we should be going in today's world. Personally, I kind of like 5. But there's some thought, well, that's 3 times as much data. Isn't that too much data? Yes, it is 3 times as much data. Yes, we do charge a little more when people send us 3 times as much data. I'm not just saying that I like 5 minutes just because we get more money that way. I think that's how I would look at things if I was running a system today. But 15 minutes, like I said, 90% of the systems are there. And today, with these ability to delve into these details in the 98s and 99s, that makes the 15 minutes actually all the more okay, I guess, right? What I don't recommend is 1 minute RMF intervals. We do have customers running 1 minute RMF intervals on some systems. I think that's overkill today, and that can be now you're talking 15 times as much data, so that can be a bit voluminous in some cases, especially depending on the number of things like coupling facility structures and volumes. I think I already said this. Also, the 99s and 98s are not that large relative to your modern systems. So record the 98s and 99s. If you happen to be Pivoter customers, then add them to your daily transmissions. And if not, make sure you have some reporting for that data as well, so that when you have a problem, you can go delve into it. This is the details that I promised you. I'll let you read this at your leisure. And then this is the promised final slide. So pretty much right on top, only seconds late. So the session code is 5L, so please do fill out your session evaluation. And if there's any more questions, I'll be happy to talk about this for as long as you want to.
I don't see any other questions in the chat, Scott. Great session. As Scott said, this is session 5L. Please remember to submit your session feedback and have a great rest of your day.
Thank you,
Thank you,
everyone, for
Scott.
coming. Sure thing.